where I had the wire hooked up to an ammeter. It was analog, so it was looking for a needle deflection. And I did this and I saw the needle deflect. So I induced a current. When I tried it again, I felt good about that. It worked, which for physics demonstration, good news. So I tried it again when I was in Charlotte. Didn't work at all. Zip, zero, nothing. And so either I just happened to be in the right spot in Columbia, South Carolina, where the magnetic field was slightly stronger than it was in Charlotte, or somehow when I moved the wire, and I think I counted for this, when I was swinging this through the air, I actually moved the ammeter, which caused the needle to deflect. Sort of a little inertia thing as the thing moves this way. But I think I took that into account, so I think it actually did. I still think it worked in Columbia, just didn't work in Charlotte. So we're dealing with Earth's magnetic field. So if you're going to use this type principle for the flying cars, you either need a superconducting surface down below, which would be incredibly expensive, or it would have to work off the Earth's magnetic field, which is on the weaker side.
So you feel like Elon's gonna have one of his whims. Like, yeah, I'm gonna pay for this city to just have a superconducting brick. Like, oh my god, that would be a pain to replace. Like, when they're fixing up the road, imagine having to fix up a road that's also superconducting.
Yeah, also to get it so this type of thing, it's called the Meissner effect. You take the magnet we have one. We have a magnet, we don't have the superconducting part, but the magnet's about that big. It has to be light for this type of thing. To keep the superconducting, you need liquid nitrogen or liquid oxygen, whichever one is the cheaper one.
Is that what bullet trains use?
I think so, but I'm not 100% sure about what they're doing with it. But they are using electromagnets to keep it up. So everything would have to be superconducting, but yeah, I don't know enough detail there.
Very cool. Just don't go to Charlotte. Stay in Columbia.
Yeah. I don't remember if I tried it here. I was thinking I did, but maybe I haven't. Maybe Winston-Salem is special. Or maybe Charlotte's just special in the wrong way. All right, let's take the next step. I have an external magnetic field coming out of the wood. No doubt dark blue on black is showing up really well in video. Into this, I have a wire that is bent.
Is it bent?
This little bit right here is one. But it just basically, and some of the master sets I call it a U-shaped wire. On top of this, I have another wire going, let's pretend this will show up. I have another wire sitting on top of the yellow wire. They're not insulated. This wire is moving at some speed v to the right. Let's go ahead and set up my hat, J hat. It is going to induce a current as this wire moves. Well, it can only induce a current if I've got a change in magnetic flux. And my magnetic flux is B times A. So as it moves out, B is not changing, but A is. A is getting bigger. I want to call this it makes a difference for the Princess Bride reference. That's L, that's W.
One question.
Yep.
Where you said the A increases, which A? The part where that box?
That area right there. So that area is the width times the length.
Yeah.
My magnetic field is B. So my magnetic flux, which is B times A, since they're parallel to each other, my area vector, if you recall, is perpendicular to the surface. So coming out that way, same direction as the magnetic field. My magnetic flux, BA, which is BWL. Now I'll induce an EMF if that is changing, because again, the induced EMF is equal to the negative change in flux with respect to time. Let's do the magnitude of the EMF. Is the negative, just magnitude, don't worry about the sign right now. It's the change in BLW over the change in time. And the negative sign is telling us the direction of basically the induced current. My magnetic field is constant, L is constant, so those would factor out. So this becomes DL, change in W over the change in time. What is the change in W over the change in time?
Speed.
Which I labeled over there as V. This is known as the motional EMF. It is the voltage that is induced by having a wire moving through a magnetic field.
And this only happens when you have two wires, one, like a bent wire, you're kind of making a box with those two wires.
It actually works. If I took something metal
Sure.
and dropped it.
Okay.
This is what we use for deriving it, but this is the induced EMF in this section right here, which is going to determine the direction of the current flowing across here.
So it's just used to find, the EMF of certain area boxes, those are things.
Sorry, say that again?
I said boxes, certain area boxes, but.
Oh, that area? It turns out that what really matters is the speed at which it's going. So the length of the wire in the magnetic field and how fast it's going. So if I just took a bar that's 1 meter long and I dropped it to the nearest magnetic field, then B is half a Gauss, L would be 1 meter, and V was whatever the speed is as it falls. So, in The Princess Bride, and I guess Micah, you probably have the best memory of this based upon reactions, see if you remember. When Billy Crystal was working, trying to save Wesley, do you remember what Billy Crystal heard Wesley say after he pumped air into him?
Now, that was in the tree, right?
Yes. Been too long. All right. Blev. He said Blev. No, he said true love. No, he said to Blev. Blev. It was just an homage to emotional EMF.
Yeah.
That's the Princess Bride reference. Now, there's a part spoiler in there, but considering the movie is, 30 years old, at least.
It's your
I told you to watch it beforehand.
It's nice to do.
All right, so let's talk about quizzes, neat junk like that. Master sets.
I think we need a new ancient paper.
Yes, we do. So we did chapter 22. This is chapter 23 stuff. So chapter 22. Today's Monday, so next Monday sounds good for Master Set Quiz. So that'll be March 18th? Is that a yes, the 18th?
Yeah, it would be.
March 18th. Homework 22, Master Set 22.
And we're still in 23? Like is what we're
Yeah,
doing.
we're still in 23. 23 will go for a bit. Because we haven't gotten to Eli to Iceman.
Is that a Top Gun reference?
Is that what?
The Top Gun reference or no?
No,
Okay.
I hope not.
That's just where I know that.
Pretty much any Tom Cruise film. What a dick. Alright, anyway, sorry. I have not met the man, it's just based on all the stories I've heard about him.
And have you posted the lab for tomorrow?
No, I haven't.
Check it.
So, by noon or I'll bring it. Because there's the lab that I want to do.
Who's the lab that you think one? Okay, the lab that you want us to do, what is the problem with it?
I'm not 100% sure that good results are based upon luck or well-done lab. That's the problem with it, but it's still one of my favorite labs.
I think we should go ahead.
We probably will. You get a 1 meter strip of aluminum-ish, and run a current through it, and you will see it go, it'll puff out. What you were trying to figure out is the magnetic field induced.
Sure, there's like machines that we're gonna be using.
Machines. Well, you've got a power supply, you've got a strip of aluminum, you got a multimeter.
Oh, well,
Okay.